Up until now, we have only taken derivatives of functions in the form y equals f of x. Functions in these forms are called explicit. Explicit functions. For example, an explicit function is y equals x squared plus 2x, and we can find its derivative, dy dx, equals 2x plus 2. Very straightforward. We use implicit differentiation to take the derivative of relations that cannot be easily expressed in function form, like the example below. We want to find dy dx for the implicit, not explicit, equation x squared plus y squared equals 9. So I'm going to rewrite this as x squared plus y squared equals 9, just to really enforce the fact that we are going to use the chain rule here. So if I focus on this first term, if I'm thinking about chain rule, my outer function is squared. So the derivative of that is 2 to the first power, and my inner function stays the same. Now, if we think about what's my inner function is x, and its derivative is 1. Now, we usually don't write that, but I'm trying to enforce a concept here. So let's roll with it. Plus, now let's focus on y squared. If I look at this as a composition of functions, the outer function is the squared. So that is 2 times whatever's inside of it to the first power. Now what's inside of it is y. Now we have to ask ourselves, what is the derivative of y with respect to x? That is going to be dy dx. And we know that equals the derivative of 9, which is 0. So notice, whenever I take the derivative of y, it equals dy dx. Same thing here, right? The derivative of y is dy dx, even in this explicit equation. So now that we've done this, we need to isolate dy dx. So I'm going to move anything that doesn't have dy dx to the other side of my equation. So I have 2y dy dx equals negative 2x. And then to isolate dy dx, I'll divide by 2y. And that gives me dy dx equals negative x over y. And so you notice even our derivative is implicit in this final answer. So remember, anytime you take the derivative of y, that is dy dx.